This is College Physics Answers with Sean Ditchko. A high-pressure gas cylinder has a volume of 50 liters, and it's full of a toxic gas, and it suddenly has a small leak out of a valve. The initial pressure in it is 1.4 times 10 to the 7 newtons per square meter, and we assume that this pressure is an absolute pressure, so we can plug it directly into our ideal gas law formula. And we make that assumption because in part C it says, to what temperature must the tank be cooled to reduce the pressure to 1 atmosphere? And so if we were talking about gauge pressure, then that would mean, what temperature should the tank be cooled to reduce the pressure to 0 gauge pressure, which would be 1 atmosphere absolute pressure. So that's what I'm using to make the assumption that this number given is an absolute pressure. So the initial temperature is 25 degrees Celsius, which we have to convert into Kelvin by adding 273.15. And we do the same to the final temperature. And this works out to 298.15 Kelvin initial temperature and 194.65 Kelvin final temperature. The initial volume we convert into cubic meters by multiplying by 1 cubic meter for every 1,000 liters. So, in part A, it says, what is the final pressure in the tank, assuming that not much gas leaks out. So initially we have initial pressure times volume, which does not get a subscript because the tank's volume is the same in both cases. The tank is not being squished or expanding, so there's no need for a VI and a VF here. And initially we have PIV equals the initial number of moles times the ideal or the universal gas constant times the absolute temperature initially. And we have PFV equals NFRTF in the final case. Now, since we're told that the leak loses a negligible amount of gas, that means that the initial number of moles is approximately equal to the final number of moles, and so we'll just call it N with no subscript. So we divide these corresponding sides of these two equations, because we're solving for PF here, and we'll substitute N in place of NF and NI. And so we have the V's canceling, and we have the NR's canceling, and then we multiply both sides by the initial pressure, and we find that the final pressure then is the initial pressure times the final temperature divided by the initial temperature. So that's 1.4 times 10 to the 7 newtons per square meter times 194.65 Kelvin divided by 298.15 Kelvin, and this is 9.14 times 10 to the 6 newtons per square meter. Now in part B, we're told that suppose that some significant amount of gas does escape. Suppose 1/10 of it escapes. In that case, the number of moles in the final case is the initial number of moles minus 1/10 of it that has disappeared out of the tank, leaving us with 9/10 left over, which is 0.9. So NF is 0.9 NI. So making the same sort of ratio between the two sides of these formulas here, we have PFV equals NF, which is 0.9 times NI times RTF, and dividing by PIV equals NI RTI. And so we have these common factors canceling here, and then multiplying both sides by PI, we get that final pressure is 0.9 times initial pressure times final temperature over initial temperature. So we expect an answer of 0.9 times the answer we got in part A, but I just plug in all the numbers given to us in the question rather than using an answer from a previous part, since we may have made a mistake in this calculation and we don't want that mistake to ruin our answer for the next question too. So this all works out to 8.23 times 10 to the 6 pascals. Pascals being an abbreviation for newtons per square meter. Now in part C, we're asked to what temperature must the tank be cooled to reduce the pressure to 1 atmosphere. And we're assuming that not much gas has leaked out. So that in that case, NI and NF are both the same, so we just call it N. And so we're dividing the two sides again, but we're putting this side over on the left here to begin with, because we know we want to solve for TF. So we have NRTF divided by NRTI equals PFV divided by PIV. The NR's cancel, and then we multiply both sides by initial temperature. The V's also cancel, and we're left with final temperature as initial temperature times the ratio of final to initial pressure. So that's 298.15 Kelvin times 1 atmosphere is the final pressure, we're told, and converted into pascals by multiplying by 1.013 times 10 to the 5 pascals per atmosphere, divided by 1.4 times 10 to the 7 newtons per square meter initial pressure, and this is 2.16 Kelvin. And part D asks us, is it a practical solution to cool the tank to this temperature to prevent leaking? Because once the tank has an absolute pressure of 1 atmosphere, there will be no gas leaking out because the pressure will be the same as the atmospheric pressure pushing in. And it's not practical, though, to cool such a large mass to 2.16 Kelvin, so it's not a practical solution.